Okay, so we're doing the plotting sample means exercise. This is the second programming exercise in week 4, expectations and the method of moments. So if you open the REPL to this exercise, you'll find this preloaded code. You're given a function that we need to complete, and this code for generating several random variables that we're going to plot using PLT here. Problem statement here gives us a formula for the method of moments expectation value, the first moment, first sample moment here, which is just the sample mean. And the problem statement tells us to complete the function called average in the panel on the left, which is that one. This function takes integer n as input. Within the function, you should generate n uniform random variables between 0 and 1. You should then calculate the sample mean from these n variables using the expression above, this expression here. Okay, so we're going to go ahead and do that. To calculate a sample mean, we would need to calculate a sum of uniform random variables, and we need to know the actual number of them. So we know the number of them, it's n. Now we need to get a sum. So to get the sum of something, set a sum variable equal to 0, and be careful not to write it as literally sum, because that's a keyword in Python and it will most likely ruin your code. So sSum is the way around that. And then once you've done that, we're going to iterate for I in range n, because we want to get n uniform random variables. And then for each iteration of the loop, we want to produce a uniform random variable. Furthermore, we need to add that to the sum. So what we're going to do here is we're going to increment, we're going to add to the current value of the variable sum the value of a uniform random variable between 0 and 1, and we do that as such. Between 0 and 1. Okay, so now for each iteration of the loop, we're going to add to the value of sum the value of a uniform random variable between 0 and 1. Okay, and once we've done that, the function is meant to return the average of those variables, so we're going to return sum over n, which is an exact reformulation of this expression here. So once we've done that, we run our code, and this bit of code here should use the function. You see here, for every yv2 value in the list yv2, it generates a sample mean of 100 random variables using the function average that we wrote. Okay, so the code is run, and as told before in the problem statement, a graph will be generated. The red points are all uniform random variables that lie between 0 and 1, and the black points are all sample means computed from sets of 100 random variables. So each of these red points are just single individual random variables, but these black points here are a distribution of a sample mean of 100 random variables, uniform random variables each. So this one here is a sample mean of 100 uniform random variables, so is this one, so is that, and they're all distributed in this way. And what this problem statement tells us to do is to consider the graph, look at the graph and consider which of the two distributions is more precisely distributed. And we can clearly see that it is in fact the distribution of these black points, which are the sample means. And what this exercise wants you to realize is that when you get sample means from bigger samples, you're more likely to get precise results versus just plotting these single individual outcomes of experiments. So you run your tests to check that they meet the criteria, and they do. You click submit, run the test one final time, and it checks out.